Today we will continue with our discussion on analysis of variance. This is the second video in a two-part series. The goal today is to study the analysis of variance test procedure. We briefly recall the setup. Xij is the random variable corresponding to the jth measurement taken from the ith population. It could also be the ith treatment applied to the jth experimental unit in the ith sample. Small xij's will correspond to the observed values of capital Xij when the experiment is performed. We assume, and these are important assumptions, the total number of populations or treatment options are going to be capital I, and the sample size in this setting is going to be the same across all samples, and it will be equal to capital J. As a result, the random variables xij's are defined for all values of I between 1 and capital I and values of j between 1 and capital J. Furthermore, we will require the very important assumption on the distribution of the xij's, which will be a normal distribution with mean mu I and variance sigma squared. Mu I is the true mean for the ith population or the ith treatment response, and sigma squared is the variance, and this remains constant across all populations or treatment responses. Note that capital Xij, the random variable, is normally distributed, and it is a very important assumption for the application of the analysis of variance test procedure. And if there is low confidence in its plausibility, one should not be using the analysis of variance test procedure described here. We will recall some of the important statistics associated to the setup. X bar I dot is the ith sample mean. This is the mean of all the responses in the ith sample. X bar double dot is the mean of the ith sample means. We call this the grand mean. The statistic capital SI squared is the sample variance of the ith sample. So we call it the ith sample variance. Next, the statistic MSTR is defined as j divided by I minus 1 times the sum of the squared variation of the ith sample mean from the grand mean. This is known as the mean square for treatments, and it is approximately the sample variance of the set of I sample means. This statistic, MSTR, captures the variation between treatments as a result. Finally, we introduce the statistic MSC, which is the sum of the I sample variances divided by capital I. This is known as the mean square for errors, and it is the sample mean of the I sample variances. The statistic captures the variation within the sample or within a given treatment. The F statistic is defined as the quotient of mean squared for treatments divided by mean squared for error. This is called the F statistic for the analysis of variance test. And to proceed with the test procedure, we need to know what the distribution of F is, and we would want to be able to calculate a relevant p-value. We begin with the distribution of the F statistic, which is the F distribution. Suppose we have two random variables, x1, which has the chi-square distribution with nu1 degrees of freedom, and x2 having the chi-squared distribution with nu2 degrees of freedom. Then we can consider a new statistic, f nu1 comma nu2, which is defined using x1 and x2. then the random variable f nu1 nu2 will have what is known as the f distribution with numerator degrees of freedom equal to nu1 and denominator degrees of freedom equals nu2. Where we won't talk more about the F distribution, it is possible to calculate its PDF and see different PDF options as nu1 and nu2 vary, but we won't be pursuing that direction any further. However, for our purposes, we would only need to know that such a distribution exists and we know how to calculate critical values corresponding to this distribution, the F distribution with a numerator and denominator degrees of freedom. It is then possible to show that when the null hypothesis for the analysis of variance hypothesis test is true, that is to say that the null hypothesis, which says that mu1 equals mu2 equals mu3 all the way up to mu I, is true, then the F statistic MSTR divided by MSC is going to have the F distribution with the numerator degrees of freedom equal to capital I minus 1 and denominator degrees of freedom equal to capital I times j minus 1. We can now calculate the p-value for the analysis of variance hypothesis test. Once we know the value of our test statistic, which will be calculated or evaluated using sample data. So if small f is the value of that f statistic, the p-value is going to be calculated as the probability that the f statistic takes values bigger than small f when the null hypothesis is true. Note that when the null hypothesis is true, we know that the f statistic has the f distribution with the given nu1, nu2, and as a result, we can calculate the p-value as the area to the right of small f under the f nu1, nu2 curve. Once we have calculated the p-value, the ANOVA test decision will be we reject the null hypothesis if the p-value is less than equal to a predefined significance level alpha, that is to say that all the means are the same, or we fail to reject the null hypothesis if the p-value is bigger than alpha, which means that at least two means are different. Now note that if we fail to reject the null hypothesis, we are saying that there is no evidence or the evidence provided suggests that all the means are equal. In this setting, we don't need to do anything more. Whereas if we were to reject the null hypothesis in ANOVA, we would be suggesting that there is statistically significant difference between at least two means. ANOVA does not tell us which pairs of means are different. To figure that out, we will need to do some more additional analysis, which could be either working with pairwise hypothesis tests or performing what is known as Twokeys procedure. Finally, we'll wrap up with providing some more insight into the analysis of variance test procedure. We can define SST, which is also called the total sum of squares, as the sum of the squared variations of the sample data from the grand mean. This captures the total variation of the sample data from the grand mean. We can show that the total sum of squares decomposes into two parts. The first part is I minus 1 times MSTR, and the second part is I times j minus 1 times MSC. We call the first part the treatment sum of squares, and we call the second part SSE, which is the error sum of squares. The treatment sum of squares captures the variation between the treatments, and as a result is a statistic that captures the variation that is explained by the status of the null hypothesis. The error sum of squares captures the variation within the treatments, which means that SSE captures the variation that cannot be explained by the status of the null hypothesis. That is, if we want to reject the null hypothesis now, we would want the variation between the treatments to be larger than the variation within the treatments. That is to say that the explained variation needs to be large relative to the unexplained variation. That is to say that if the treatment sum of squares is much larger than the error sum of squares, or equivalently, if the mean squares for treatments is much larger than the mean squares for errors, or equivalently, if the F statistic, that is the quotient of the mean square for treatments divided by the mean square for errors, is much larger than 1, we would have that the explained variation is large relative to the unexplained variation. And as a result, we would be more inclined to reject the null hypothesis. To summarize, we have introduced the F statistic. We have introduced the distribution for the F statistic, which is the F distribution. We've specified a way of calculating a p-value which would help us arrive at a test decision for our analysis of variance hypothesis test. And finally, we have analyzed what variation it is that we are analyzing in the ANOVA procedure. We will talk more about this in a later video, but this is all for now. Take care of yourselves, and I will see you around.